Swayam Prabha. Digital India. Educated India.
So earlier we had covered reverberations in rooms which were of regular shapes, parallel walls. They could be 1D long rooms or 2-dimensional rooms, or we had also talked about 3-dimensional rooms. A lot of rooms, however, big auditoriums, concert halls, and a lot of lecture theatres, they are not of regular shapes. So what we will cover today is how does sound behave if it gets propagated inside a large but irregular room. So couple of things for large irregular rooms. One, that because the walls are not perfectly parallel to each other, so the reflections keep on happening and you will have standing waves for virtually any frequency and at virtually any angle of incidence, because things are not very nicely parallel to each other. Second thing, at any given point sound moves in all directions. In parallel rooms, if you have a forward going planar wave, then it will nicely behave and reflect, and it will move in straight lines. So the propagation will not necessarily be in all directions, but in irregular rooms these reflections could happen in not reflect, because of the nature of reflections, the propagation of sound at any given point could be in all directions. Third thing, the number of modes in these rooms and the number of natural frequencies in these rooms is extremely large. It's even larger compared to some of the 3D room examples which we had seen. So at virtually any given frequency, if you move from one point to other point within a very small distance, you will see moving from one node to other node to other node. In last class we had seen, because it's like a more or less a rectangular room, for low frequencies the distance between two nodes, at least in this room which has parallel walls, it's a nice rectangular boxy room, at low frequencies the distance or the separation of nodes at low frequencies, 125 hertz we had seen, is not very small, but in irregular rooms that may not necessarily be the case. So if you combine all these 4-5 effects which I had mentioned, then the sound field in such a room is called a diffuse field. It's called a diffuse field. So we will develop some relations how sound behaves in these kind of enclosures. So it's large irregular rooms. So what I will do is I will introduce a couple of terminologies. So the first concept I will introduce is develop a relation between energy density in the room, energy density, and the sound pressure level. And this I have taken from some of the earlier class notes. So it's just a mapping. So I'll define a term D average is P average square over rho naught C square, and this is sound energy density. Is D average. So the units of this guy are watts second. Watt second is energy or joules, right? And because it's density, it's for every cubic meter. Couple of things to note. P average is the average of RMS pressure in space and time. What does that mean? So if I have a microphone, when I am playing music or people are talking, the microphone is sensing some pressure level. So I position a microphone at a point and I record data for let's say few minutes, 1 minute, 2 minutes, and then I take the average, the average of the different RMS values. So for first 1/10 of a second I find the RMS, second 1/10 of a second I find the RMS, and then I average it out. So that is averaging the RMS pressure in time. Now I move my microphone to a slightly different location and then I do the same exercise. So then I am averaging it in space. So this guy is average in both space and time. So you measure for a little longer periods of time at couple of locations and then you get this P average. And it is again the average of RMS pressure. It's not the peak pressure, it's not the minimum pressure, it's the average of RMS pressure. And of course, rho naught is air density and C is velocity of sound in air. That's my sound energy density. The second concept I will introduce, and this is a new concept, mean free path. Let's consider couple of walls in an enclosure. I have incident sound, it gets reflected by this surface. So it comes and hits another surface, it gets again reflected, and it gets again reflected, and so on and so forth. The mean free path, I will define it as letter D, and this is average distance between two reflecting surfaces. So this distance could be D. This is reflecting surface 1 of absorption coefficient alpha 1. We will define and explain what these alphas are later, alpha 2, alpha 3. So between two reflecting surfaces, average distance through which the sound travels is D. And if I have to compute the value of D, it is 4V over S. How did we get this relation? So V is volume of room, S is total surface area, I mean reflecting area. This could be in meter cubes or feet cubes. This could be in meter square or feet square. So the first time there was an acoustician, his name was Knudsen. So in 1932, he did some experiments. He computed experimentally the value of D. So he designed 10, 12 different types of closed spaces. All these closed spaces were irregular in shape and they were very significantly different from each other. So it's not that they were slightly different, they were very significantly different. And what he found was that the value of D comes to 4V over S. Later, based on some statistical principles, people also did some studies and from a theoretical standpoint validated the same expression. So this expression D equals 4V over S has an experimental basis and also a statistical basis. The value of D could be either in feet or in meters, but you have to be just consistent. And the reason I am saying that is that because it's a relation based on statistics and experiments, we have to be careful about unit. So we have talked about D average. The second concept we introduced is mean free path, which is D. Now we will introduce another thing called sound energy absorption coefficient. Okay, and this is alpha. Alpha is absorbed energy by a reflecting surface divided by incident energy. And this I average it over all angles of incidence, because the absorption coefficient will change as my angle of incidence is changing. So whatever energy is being absorbed for different values of incident angles, I average them up and I get value of alpha. This is an experimentally, so you find this value alpha for different materials through experiments. The other thing you may want to know is that this value of alpha is strongly dependent on frequency. So it changes with frequency. I will give you two examples. So the handout which you have today, I extracted these two pieces of data. For example, this wood panel which is 2 to 4 inches thick, alpha equals 0.3 at 125 hertz, and same thing goes down to 0.10 at 4000 hertz. So they change significantly with frequency. And then I will give you another counter example, carpet. It could be 5/8 inch thick, alpha is 0.2 at 125 hertz, and in this case it's going up at 4000 hertz. So whenever we talk about alpha, the natural question is that alpha at what frequency? There are some materials where alpha is more or less constant over the frequency range, but most of the materials, they have very strong frequency dependent behavior. So alpha always has to be talked in context of a frequency number. In general, when people don't specify alpha, then you may assume with a little bit of latitude that it's maybe for 500 cycles per second. Third thing I wanted to mention is that this is a ratio of energies. It is not a ratio of pressures. Okay, so it's a ratio of energies. So if I have a irregular room which has lots of reflecting surfaces, then for that room I can compute an average alpha, and I can do that in such a way that I take S1 is the first reflecting area, alpha 1 plus S2, alpha 2, their n surfaces Sn over total reflecting area in the room, where S equals S1 plus S2 plus Sn. Question: what would be the alpha or reflection coefficient of a window? Open window, 1. So if you have windows in your rooms, you should still account for those by prescribing an appropriate value. If it's closed, then you have to, or if it's open, then you have to make it 1. So alpha window equals 1. If there's a room, so this is for an empty room. Okay. If there's a room with people sitting in it, then again the handout which you have, it provides values of alpha for individuals, whether they are sitting or standing or they are on a chair and so on and so forth. So if there are people sitting in it, then we can say approximate average alpha would be S1 alpha 1 plus S2 alpha 2, it's an alpha n, plus alpha person times number of people sitting in the room or standing or whatever over S. So this is with people. Typically alpha P exceeds 1, 1.5, sometimes it goes up to 7, 8. So we have talked about three concepts: sound energy density, mean free path, sound energy absorption coefficient. A lot of times it is also called sound absorption coefficient. So just be aware. So using these three concepts, we will develop a property of a room which is large and irregular, and this property is called reverberation time. And we will designate it by a letter capital T. Couple of points. It is a metric. One of the metrics. Metric is a measure of large acoustic spaces. To figure out whether an auditorium sounds good or bad, this is one way of objectively calibrating yourself and saying that yes, this room sounds good, this room does not sound good. Second thing, T is the time taken when SPL, that is the sound pressure level, which is fully developed, decays by 60 dBs. What does this mean? You have an auditorium or a lecture theatre L7 and you start the sound system there, or if people are talking, let that start happening, and at a particular point you place a microphone and you will see that after a certain period of time the sound pressure level will stabilize. Once it has stabilized, then you turn off the source and then sound pressure level will start decaying very fast. So the time it takes to start from that P naught condition to P naught minus 60 dB, that time is called reverberation time of that room. What is 60 decibels in pressure? Two pressure values are off by 60 decibels. It means what is the ratio of pressure in absolute? 1000. 60 dB corresponds to PT over P naught is 1000. And if I am computing the ratio of energies, ratio is 10 to the power of minus 6. Using this understanding, we will start now doing some math. So again, we will draw three surfaces. All these three surfaces are reflecting and they also do absorb some sound. So let us say this absorption coefficient of this surface is alpha 1, this surface is alpha 2, this surface is alpha 3, such that the overall room's absorption coefficient is alpha bar. That is my incident sound. It gets reflected again, gets reflected again. The intensity of incident sound is D naught. What will be the intensity of sound after it gets first reflection? D naught times alpha got absorbed. What is remaining? 1 minus alpha. This guy becomes T naught 1 minus alpha square. This is D naught 1 minus alpha cube. These are the, so in a statistical sense, okay, so these are alpha, this is the average alpha for the room. In a more precise way, yes, you are right. It will be D naught times 1 minus alpha 1 times 1 minus alpha 2 and so on and so forth. But in a statistical sense, I am just using alpha average, alpha bar. What we will do is construct a simple table. First column time, second column delta T, third column value of D. Okay. At T equals 0, delta T is 0 times 4V over Cs. T is 0. This is D1 equals D0. That is 4V over C. At first reflection, so actually this is my reflection number. Okay. At first reflection, delta T is 1 times 4V over Cs. This is D naught times 1 minus alpha bar. This is D1. Second reflection, delta T is 4V over Cs, and this is D2 equals D naught 1 minus alpha bar whole square. Nth reflection, it is N times 4V over Cs, Dn equals D naught 1 minus alpha bar N. Now we know that we can also write N as total time elapsed, which is T over delta T, and that is T times Cs over 4V. So with that understanding, I can express at any given time the sound energy density is dt equals d naught 1 minus alpha bar times Cs over 4V times T. I can again reframe it as exponent log 1 minus alpha bar so if I plot dt with respect to time, I get this kind of a relationship, an exponential decay relationship. So this is, in regular rooms we had developed a relation for envelope of decay. In this case, the envelope of decay is also giving you the exact value of pressures at different times, of sound intensity at different times, because reflections are happening all the time and the overall field in the room is diffuse. The other thing is, we made this jump N equals T over delta T, and this is because again the room is irregular, so the values of delta T do not increase in quantum, they are continuously changing. So this is also a continuous variable. In the earlier case where we had parallel walls, this T was changing from one, this reflections were happening and T was progressing in one quantum, second quanta, third quanta, and so on and so forth. Here it's a continuous variable. So that's my envelope of decay. We know that D is related to energy, so it is directly proportional to P square, pressure square. So I can also say that pressure in the room will also decay in a similar exponential factor such that it is P naught E log 1 minus alpha. But what will be the value of Cs here? Cs 8V T. So instead of 4, I am putting an 8 here because the relationship between D and P is a square relationship. So I label this expression as 1. We know that sound pressure level in decibels is 20 log in base 10 P RMS over P ref, where P ref equals 2 into 10 to the power of minus 5 newtons per square meter. So what is it that we are trying to do through this entire exercise? We are trying to develop an expression for reverberation time. So we don't have to forget that. So if T equals T, right, which corresponds to reverb time, then SPL at T equals 0 minus SPL at T equals T What is the difference? 60 decibels. So I put this relation in this equation, and what I get is 20 log P RMS over P ref at t equals 0 minus 20 log P RMS over P ref at t equals 60 dB. And I can rearrange this as 20 log P RMS at t equals 0 divided by P RMS at t equals t is 60. What is P RMS at t equals 0? P naught. What I get is 20 log. So basically what I get is this thing. E ln 1 minus alpha bar, and the whole thing is raised to the power of 8V times t. Can everyone read this? I did some micro typing there, or writing there. It could be read? Okay. So just to make sure that you have read it correctly, 20 log 1 over exponent natural log 1 minus alpha in parenthesis, the whole thing raised to the power of Cs over 8Vt. So now I do some mathematical manipulations. I get 20 log E minus ln 1 minus alpha Cs over 8V times t equals 60. So now I take the log, and what do I get? 20. I take log of this guy, so I get minus ln 1 minus alpha times log of E times Cs over V t equals 60. So I get 20 log of, this is log is in log 10, base 10, so log of times 0.434, that's log of E divided by 8. So I am pulling these three together, times minus ln 1 minus alpha times S times Ct over V equals 60. So this entire thing becomes 1.086 times this entire expression times Ct over V equals 60, and I call this expression as A prime. Is A prime a positive number or a negative number? Because 1 minus alpha is less than 1. So this A prime is positive. So essentially what I get is reverb time equals, I can move everything on the right side, 55 over V divided by A prime C. And A prime is called absorption unit. The name is absorption unit, it is not a unit of, the name is absorption unit, and the unit of this absorption unit quantity is meter square in SI system, and feet square, but more popularly it is also called Sabine, Sabin, in British system. Sabine is feet square. And A prime is called absorption. A prime is a property of the room, because what is it? It's basically S times a function of alpha, and essentially what it tells is how much sound is overall, in an overall sense, getting absorbed by the, say that T is 50 times V over A prime C, and we can rewrite, because C we know the value of C, so we can rewrite the same equation as T equals 0.161 V over A prime. And this is a very famous equation in architectural acoustics. It's called Sabine's formula. It's named after a person, obviously Sabine, who in 1898 in Boston, he measured coefficients, this reverb time of this formula should work in both. So you have to change it. Yeah, so this is for SI system. Yes, you are right. But you can change it. This constant will change. But the formula is will still be called Sabine. So what Sabine did is, hold on. What Sabine did is that he took an axis, and he was computing with respect to, he was essentially plotting this V over A ratio, and what he found was that this is a hyperbolic relationship. So from that he said that, okay, I can extract this value of T. So he was doing that numerically. Now he was probably not playing with this 0.161 parameter, because that comes out naturally once you plot this entire hyperbola, then that thing comes out. So this is it looks a very simple relation. There are only three terms in it, T, V and A, and it looks very deceptive, but it has a lot of substance in it. So one thing is that as V goes up, T will go up. Second, as alpha goes up, what happens to T? It goes towards 0. Why? Because you have in this A prime, you have logarithm 1 minus alpha. So this goes towards minus infinity. The third thing, remember, there's this relation is dependent on frequency. So each room will have different reverb constants for different frequencies, because alpha depends on frequency. So don't forget that. In this entire analysis, we have only assumed that sound is getting absorbed only on the reflecting surfaces. As it moves from one surface to other surface, during the movement of sound from one surface to other surface, nothing is getting absorbed. But in reality, air also does attenuate the overall sound pressure level. So this formula needs a little bit of calibration to account for absorption of air. But even without that, it's fairly good relation. So we had talked about how do you measure T. First thing is you excite a room with some sound source, till SPL is stabilized. But it takes a little bit time for the sound pressure level to converge and become flat, and then you switch it off, the sound source. So what you get is something like this. So here if I am plotting P over P naught in decibels, then when I am exciting, it becomes stable after a while, and then I switch this thing off, and the sound pressure level decays, something like this. So if this is my reference, which is 0 dB, I am recording data, and this is minus 60 dB, then this value of time is my reverb time. And this approach of measuring T is called switch off method. I want to make a couple of qualifications in this entire discussion or analysis. One is that this theory is good to the extent that sound field is what? Diffuse. It's well distributed throughout the room. So that is one, that we need to have a diffuse field. Second thing is that the room should not only be irregular, but it should not also have focusing elements. What do I mean by focusing element? For instance, I have, let's say, light, and then I can have a concave mirror which will focus light in a particular way. Similarly, I can have surfaces which focus sound at particular locations. So I do not want to have any focusing elements in the room. With that will kill the smoothness of SPL distribution in the room. So I don't, they could even be a little bit curved, but they shouldn't overtly focus in one particular area or a zone. Third thing is that the total absorption coefficient should be small or moderate. What does that mean? That if my alpha bar is fairly large, then it does not take a lot of reflections for the sound to decay to a level which is not measurable. So alpha has to be not too large. It could be fairly small also, but it does not have to be large. For instance, if there is a room and all the windows are open and it only has windows in practical sense, then this reverb time and all this discussion becomes meaningless. So one way to quantify that the room's absorption characteristics are moderate or small is that V over log minus 1 minus alpha S is V over alpha S is greater than 1 meter. Some way to quantify. So if you go to lecture hall complex, you hear a lot of echoes, especially in L1 and some of the larger rooms. Right? Whenever a professor is teaching, the sound is not clear. And I think the biggest challenge there is the reverb time. It's too large. What I also wanted to show you is a couple of slides which will be helpful. Just for record, this is the picture of Mr. Sabine. What you are seeing here on this plot is typical recommended reverb times for different applications. For instance, a classroom where most of the frequency content is in the bandwidth of speech. About 0.8 seconds is the optimum time. So if you have a classroom where reverb time is significantly larger than this, then the speech will not necessarily be intelligible, won't be understood easily. Similarly, theaters where you have a mix of music and speech, they need a little larger reverb time. And then concert halls where you want to have a good amount of reverberation, the time is in excess of 2 seconds and so on and so forth. So this is another chart. It shows in some quantifiable ways. For speech, 0.8 to 1.3 is a good reverb time. 2 seconds is certainly unacceptable. Even if I am in 1.4 to 2, it may be poor or fair. And for pure music, I need a little higher reverb time. If the reverb time is too low, then sound does not excite the human emotion as much. This is there. Diffuse field.
Yeah, the field is diffuse. Like, are you considering a single 1D source, like a wave?
You can have. It could be omnidirectional. You could have, because the point is that because you have irregular rooms, so even regardless whether it's omnidirectional or unidirectional, at the end of the day, sound will be moving in all directions at all frequencies at all.
In case a window is open, and after some reflections, it goes to the window. If a unidirectional source is there, so then in that case, what will be the reverberation time?
So again, because of the nature of irregularity of the room, by the time it reaches, unless you are directly projecting sound towards the window, that's a totally different case. By the time it reaches, by that time the sound field should have become diffuse enough. So there's no very hard objective cutoff that, but this is an approximate answer to your. What happens if the reverb time is too low? Let's say we are talking in this room, and if the reverb time is too low, It's, let's say, 0 seconds. What does that mean physically? What that means is that the person who is speaking, he has to make more effort in making himself or herself heard. So you also need some reverb time. 0 is not good because that requires more power for the person or for the sound system. But if it is too high, then if I say cat, by the time I am saying ta, C will also overlap with ka. So it will become confusing. Another parameter which we can extract if we know the reverb time of a room is called bandwidth or Q of a room, and we will talk about it. Let us say we have a spring mass damper system, F equals Kx plus Cx dot plus Mx dot dot, and if I plot the response of that kind of a system, I get something like this, right, where this is my omega and this is my amplitude, right. This could be some transfer function which is a function of this point is what? Natural frequency. So bandwidth of this kind of a system is defined as a range of frequencies between which the power goes down or the value of H goes down by a factor of 3 dBs. So this is 3 dB and this is, let us say, H naught, then this will be what? H naught over root 2. So associated with this is a parameter called delta omega. Delta omega is called bandwidth. Omega over delta omega is called Q. It's an industry standard term. Even in vibrations you hear this term Q. What is the Q of the system? So if there is no damping in the system, what does Q become? Infinite. Q becomes infinite when there is no damping in the system, right. So Q is also kind of a reflection of how damped the system is. At omega equals omega naught plus minus delta omega over 2, my energy is half the direct variable H, which could be pressure or velocity or displacement. H is 1 over root 2. So this is the bandwidth. Now the question is that if I have a room and there is a diffuse field in it, what is Q of that room? So we will try to use this concept and also the idea of T and try to figure out what is the value of Q of a room. So there is an intermediate step to get to that answer. So let us say you have a signal H naught E minus gamma t. The Laplace of it will be Hs equals H naught over S plus alpha. So we will plot this. And we get something like this. This is my H naught. This is my, if this is H naught over root 2 alpha and this is alpha, then bandwidth is 2 alpha and Q, oh I am sorry, this should be gamma. Yeah, I am sorry. Gamma. This is also gamma. So Q is what? Omega naught over 2 gamma. In this case it is infinity because omega naught is 0. This is my omega naught. But the point is that if I have an exponential decay form, then my bandwidth is 2 gamma. So now we go to a diffuse room, and in a diffuse room my HT signal is essentially, we had developed it, right, is H naught E minus gamma t cosine omega t. What this means is that if I have a room, and if I started playing a tone of omega naught in that room till it became stabilized, and then I turned it off, right, then the signal in the room will decay in such a way. It will still be cosine omega t, but it will decay over a period of time in an exponential way, e to the power of minus gamma t. That is what it means. This should be a little not that sharp. So, my center frequency is omega naught, and this is h naught over 2 gamma root 2. This is h naught over 2 gamma. So, essentially my bandwidth of a room is 2 gamma, and Q associated with the frequency which is getting excited in the room is. Now, in case of our room, we know that gamma is what? Minus ln 1 minus alpha bar times Cs over 8V. Remember, it's 8 because we are not plotting in this case the energy, we are plotting the fundamental variable, pressure or displacement or whatever. So, I can use this and these to figure out the overall Q of the room. We will do a very quick example. So, let us say my t equals 2 seconds, this is example. Omega naught is 100 hertz, then what is bandwidth and what is Q? So, we know that gamma is ln 1 minus alpha bar Sc over 8V. This is basically A prime C over 8V. We also know that T is 55V over 8T AC. A prime C. So, this gives me A prime C over V, which I will later introduce here. AC over V is 55 over T. So, now I put this here, and gamma is 55 over 8T, and that gives me gamma equals 55 over 8 into 2 equals, the number comes to 3.4 seconds. So, gamma is 3.4 seconds, and delta W was 2 gamma is 6.8 seconds. Gamma is radians. Yes, you are right. And that translates to 1.0942 degrees. So, Q equals omega naught over delta W equals 100 over 1.094. That's approximately 90 hertz. What it physically means is that between 90 hertz and 110 hertz, the room will sound very shrill. If I play a tone, the room will, the decay of energy will be by a factor of 2 between 90 and 110 hertz. That's what it means. So, if this band is very thin, then the room will be very shrill, that band, because if it will pick up, then it will be very shrill. If this band is a little bit wide, then it will be very smooth transition of energy. That's what it means. We will do 3 examples of reverb time, how it is used in industry applications. So, one is, we already talked about finding the constant of a room and using the constant to design a room accordingly. So, T helps us in designing acoustic spaces. In your assignment, there's one question where you will be expected to tune the characteristics of a particular room such that you acquire a T of, I think it's like 0.7 seconds. So if you have a target value, then you can architect your room accordingly so that you hit your target value of T. So that is one. Second one is, okay, so in this context, again, it's dependent on frequency. There's no reverb time which works for all frequency ranges. So you have to design for a particular frequency or a set of frequencies. Second thing is, it has to be irregular room, it has to be fairly large enough, and if it is not large, if it's a small quote unquote regular room, then the Sabine's approach, it does not work that well. So in that case, there are some other approaches where they take ratios of reflected energy and direct energy, and then they try to optimize that particular parameter. But in large irregular rooms where the sound field is fairly diffuse, reverb time does a fairly good work in terms of optimizing the acoustics of them. The second thing is, you can use T to measure alpha of a particular material. How do you do that? So way back in the course, we had talked about one dimensional long tube which has unknown reflective impedance, and using the Kund's approach, we could figure out the reflectivity or reflection coefficient of this material, right, and also the phase of the material by sweeping the microphone along the length of the tube. But that approach is good only if your sound is hitting in what direction? In normal direction. So if I surface this and it's hitting like that, then that is the way to develop, get reflective coefficient of the material. If I have to develop an understanding for different incident angles or in an overall average sense, what is the reflection coefficient of the material, then we can use T to find out the value of alpha. So we'll quickly cover that. Aim is to measure alpha of unknown material. So step 1, we take a fairly diffuse room which does not have a high absorption characteristic, and then find the reverb time of that room without this material in it. Okay, so find T without unknown material. So T equals 0.161 V over A prime, and if I do the math, I get minus ln 1 minus alpha bar equals T over 0.161 Vs. S is the surface area. I know surface area of the room, so I can get log alpha from this relation, and I can also get alpha bar for the room without the material, and that is basically 1 minus E minus T over 0.161 Vs. Okay, so I know alpha bar for this room. From T I can figure out the alpha bar for this. Then step 2, I do the same measurement and I find alpha nu. So in the same room, now I place this material, I know the surface area of the material, and I find alpha nu. So from alpha nu and from alpha, I can extract the value of alpha of the material. How do we do that? So that's what exactly what we'll do. So alpha nu is basically alpha I Si plus S of the material. I is only for the room alone. S material, alpha material, and divided by S plus S mat. So this is basically Si alpha I over S plus S mat plus S mat times alpha mat over S plus S mat. I do not know alpha mat. I know everything else. Also, I do not know this quantity as one single entity. I do not know this also, right? I know alpha I, but I don't know this entire thing by itself, because this is different than the alpha of the room. So what I do is Si alpha I over S times S over S plus S mat plus S mat times alpha mat over S plus S mat. This is, what is this term? Alpha bar times S over S plus S mat. So I know this S mat over S plus S mat times alpha mat. So now I know everything. I know all these blocks, and this is the only guy which I do not know. So I can figure out alpha mat in this way. So this is another application. The reverb time has usage in terms of designing architectural spaces, also characterizing materials, also developing targets for different types of rooms. Once again, it's dependent on frequency, and the choice of what is the right reverb time for a particular acoustic space, it depends on how we are going to use that space. So if I have a room where I will use it only for purposes of talking, then I have to shoot for one particular value of T. If I have to use it only for music, then I have to use maybe another value of T. If I have to use for a mixture of applications, then my target has to be different. So that's all I wanted to cover today, and then we'll meet next.